I wanted to give you the weekend, right? For the momentum test, I could have given it today. My thinking is, if you want it today, it's up to you. My whole point of giving you the weekend is to give you extra time, but some people are complaining just because I've delayed it. Doesn't make sense. Take the extra time. Okay, if I'm getting complaints because I'm delaying tests, that's ridiculous. If you want me to give them one after another, easy for me to do. I can't believe it, but whatever. I'd be grateful.
Yeah, I'm going to be grateful.
Yeah, remember momentum test on Monday. Yes, I know I still have to give you a breakdown. I got the time to do that when you're doing the lab. I can just do a little write-up and then hand it out to you. But complaints, complaints, complaints. Okay, I'll go over the work in a second here. 7 and 8, page 202.
Well, you know, as I say, what there are no problems. Bro, I failed. It's not sharpener. No sharpener. Is that a 5-year sharpener? If each test was the same. If each test was the same.
You mean each assignment?
I know, like each test is just really like the same. Not say this last one's like out of 48, this one's out of 37.
Oh, each test. Yeah. Unless I feel otherwise, I can weigh it differently, but in general, yeah. Okay, let's go over 7. Okay, so remember, these problems here are translational equilibrium. Now, I had you work on these along with the rotational because you need to still apply the condition for translational with the rotational problems. So you still need to be very familiar with these sorts of problems because they're usually, not always, but they're usually part B or the second part of the rotational problems. So let's go through this one. That's the ceiling. You know what? I'm just going to separate
Hello.
Okay, so we know how to apply that rule. That's 60 degrees. That's 30 degrees. Okay. I don't know what FG is. Slightly different. I'll call this, instead of, just to avoid extra subscripts, I'll call it F2. F1 we have, so we know this is 96. That's my F1. Okay, I'm going to draw in my Y components. Those are going to be in purple. So let's calculate what these X and Y components are for the F1, the 96 Newton. I'm going to just skip that. You know how to do that? That is pretty easy by now. This is 48. This is the cosine, 96 times the cosine. And the Y component is 96 times the sine. Okay, make sure you get the directions correct, right? The X component for F1 is pointed to the left. The X component for F2 is pointed to the right. And then the Y components for F1 and F2 are up. Okay, I'll write in the components for F2. So for F2, we have F2 times the cosine of 30. And then for F2y, we have F2 times the sine of 30. Okay, so now we can write our conditions. Okay, I always start off with the X. So we already have the X component for F1. So we have F2 goes to 30 minus the 48 because that's pointed to the left. It's pointing in the opposite direction, so it's subtracted. Put the 48 on the right. You get F2 is equal to 48 divided by 0.866. So this works out to be 55.4 for F2. Okay, we'll come back to that. We need to find FG, so we still need to figure out what the Y components are. Okay, so for the Y components, we have these two. We have the 83 that's up and the F2 sine 30 that's up. So they'll be added. And then FG is pointed down, so it'll be subtracted. I have my F2. I just figured that out over here. That's my F2. I can plug that in. And I put FG on the right side. And that gives me my FG. So what is that? I don't have a value for it. So that works out to be 110.7. 1 point, I'll just say 1.1 times 10 to the 2. Okay. Take a look at 8. 8's just a, you've done it before, it's just a little bit, again, a geometry problem. Okay, so I'm going to draw the triangle. We don't know particular angles yet. We can find them from the sides that are given. Okay, we'll come back to, I'm not worried about the forces yet. We'll come back to, we need these angles. We need this angle here. And this angle here. Okay, and that'll give us the corresponding angles on the bottom with respect to the x-axis. This angle here is equal to this angle here. This angle here is equal to this angle here. So find the angles inside the triangle. We can do that because this is a right angle triangle. Okay, and we have the sides. So this angle here, okay, this side is opposite this angle. So let's label it. Label these angles. Okay. I'll call this, what did they do? Sure, call this theta 1. Call this theta 2. So the sine of theta 1, again, this side is opposite it, is equal to 3 divided by the hypotenuse. That's the hypotenuse. That gives us theta 1. And then similarly with theta 2, that's the opposite side for theta 2. So theta 2 is 63.5. Once you've got this angle, you don't even need to use the sine. You can just subtract 90 from 26.5. So Okay, so now I'll redraw it with the angles, the corresponding angles. Once you've got the angles, then it's just a problem that you've already done before. So this angle here on the left, that's my theta 2. That's 63. And on the right, that's 26.5. Okay. I'll call this F1 and this F2. Okay, so that's right in our expressions. So for Fx, F1x, this is F, I'll do it in red. This is F1 cos. This is F1 sine. This is F2 cos. This is F2 sine. Okay, so now we can start writing our expressions. Same as before. And your FG, again, you don't know it. So it's very similar to this problem here, right? You've got your F1. You do have this. So it is similar to the problem above. So that's 55. That's 55. That's 55. Okay, now we can write our expressions out in full. For the x, start with that. We have 55 times the cosine minus F2 cosine. Okay. Give me a sec here. Anyways. So I'm just rearranged for F2. That works out to be 110.4. And then for the y, we have these two in the same direction, so they'll be added. And this is in the opposite direction, that's going to subtract. And then you're going to substitute what you now know for F2. You're going to substitute it into that. Give me a second here. F2. This should be 0.895. And this should be 0.446. So FG works out to be 123 or 1.2 times 10 to the 2. Okay. Yeah. I can give it to you in a second. Yeah, I think I've got an extra. Yeah.
So for this, you use for like calculating the angles, you can use like the ones with m. That's like meters behind it.
Yeah, because it,
But like for the actual force itself, you have to use the ft1 given.
yes.
Okay.
Yeah. Mm-hmm.
Instead of sine, I use cos and tan.
Perfect. You got options. Yeah, because it's you got all three sides, so whatever you want to use.
I'm getting 20 for the first angle. I got 26.4. For the second, I got 62.4.
Let's look at it later. I'll see your calculation. Should work out. Okay, so next, page 210. There's 1 and 2. Okay, so it's a wrench. You're exerting a force perpendicular, so the angle is 90 degrees. It's one thing that stands out for me. The torque is given. So the torque is equal to F times the sine of theta, sine of 90, times the L, the distance from where the force is acting to the pivot. Well, we've got the torque in Newton meters, that's 45. We don't have the force. We have the angle, and we have the length in centimeters. You want to convert that to meters. So 129 newtons, or 1.3 times 10 to the 2. Okay, that's number one. Number two. read it over again. This is a two-part, so you will need to use your condition for translational equilibrium part B. Okay. So it's important you understand something. This has actually been simplified for you. It says it's negligible mass. That means next to zero. So the weight of the beam doesn't contribute. So that's 40 degrees with my unknown force, Ft. And the only downwards force is the 400 newtons. Acting at the center. So we have a full-length beam. And the weight's acting at the halfway point. One half L. Ft is acting at the full length. So what's the magnitude of the tension? So remember this before we even start. Let's remember something, that there are forces acting at the hinge. And we're going to come back to that in part B. I have Fv. And I have I have an FH. Okay, we'll come back to that. This set of forces, FV and FH, do not contribute to torque. Torque is zero. Torque is zero because I'm assuming the pivot's here. Put a little triangle where you think the pivot is. So place it, in general, place it to wherever it's attached to the wall, either the left or right side. You can place it wherever you want, but all measurements have to be based from that pivot. We're assuming, well, I know from experience, place it, in this case, it's attached to the wall on the left side. Place the pivot on the left side. What does that mean? Why is the torque zero? The distance from where the forces act to the pivot is zero. And torque is force times distance. So if the distance is zero, the torque is zero. Yeah. Oh, thank you for reminding me. No, it's not centered. That's better.
Full screen thing.
You sh-
I think your mouse is what you do. So like you gotta aim your mouse.
Yeah, I'm trying. It's not moving over to the right, so.
No, like go back out. I think. And then center your mouse in the middle. And then try.
Thank you. Yeah.
How do you know that torque is zero?
The distance, remember torque is force times the sine. Forget about the sine. The sine is, it's basically force times distance, right? If D is zero, torque is zero. What is D? D is, if we zero in, let's look, I'll erase this in a second because I need the room, but that's the end of the beam. Okay? If we take a look at FV, to find the torque, we always measure the distance from the tail, the distance from the tail of the force to the pivot, measured along the length of the beam. How far is that tail from the pivot? It's hovering over it. It's right over it. So the distance is 0. There is no torque due to this. The distance is 0. Yeah, I'm just explaining. Okay. This is not 0. Let me redraw it. Let's say the force was hovering. Let's say the force was here. Pivot's here. Pivot's there, right? This is an example where the distance is not 0. I don't know. Let's say it's 1 meter. This is kind of sloppy, but. Okay, from here, you measure always parallel to the beam. From here to here, that's 1 meter. It's not 0 anymore. If I move it back over here, the distance is 0. Torque, again, is essentially just force times distance. The D is 0. 0 times anything is 0. Are you going to be able to rotate the beam with this? If you put a force there, can you rotate it this way? It'd be hard, but yes, you could, right? You could pull it. If you put the force there directly over the hinge or pivot, could you rotate it? No. No torque. Torque. What does a torque cause the beam to do? It causes it to rotate. So if it can't rotate it, there's no torque. It's a good question. Everyone got that? I'm going to erase it. I need the room, so. I guess I could put it below. I like that. Anyways, I want the space. Okay, let me erase this now. Everyone got it? Okay, so we have two torques. We have a torque due to this force that if it was acting alone would rotate it in this direction. Well, in this direction. Counterclockwise. So that's a positive torque. The torque due to that is equal to Ft times the sine of 40 times the full distance. I don't know what that distance is. We'll call it L. We don't need to know. It'll cancel out. It has to be, in order for that beam to sit there and not rotate, okay, there has to be another torque to balance that. So this is, I'll call it torque 2. Torque 2 is equal to 400. And I'm not finished with the sine. I'll come back to that in a second. Times the sine of 90. It's acting at half the distance. Okay, now we always have to finish it with the sine. So let's ask ourselves, if this force here was allowed to act freely, it would pull the beam this way. Remember, the beam, you can think of the beam as being fixed. The beam is fixed. Think of that as a hinge. Think of the hinge as being fixed and the beam simply being able to rotate with the hinge fixed. So this force here would rotate it this way, clockwise. So that's a negative. Okay, so what do we have? In order for this beam to not rotate, this condition has to be followed. So add the torques, making sure that one of them is negative, which we did. The first torque is Ft times the sine of 40. Second torque has to be negative. They have to balance each other to give 0. Sine of 90 is just 1. Okay, so the L is common to both terms. We talked about this. There's a common factor in every term in the equation. It cancels out. Okay, Ft times the sine of 40. So works out to be 3.310. Okay, that's part A. So it's important you understand something. If it's a two-part torque problem, the second part needs the first part. You need to know what this force is. So you need to apply this condition in part A first. Always apply the condition for rotational equilibrium first. That will allow you to solve for, in this case, Ft, which will then allow you to solve for the forces Fv and Fh. You need to do part A first. Part B, what is Fv? What is Fh? Okay. I'm going to redraw it for you. I guess I could go back up here, but I guess I could circle it, lasso it. Need a little bit bigger. There you go. Okay, so let's draw in our components just so you can see what's balanced. I try to draw these color coordinated. So this is my X component, my FTX. The X components are in green. That's to make you aware of the fact that these two components are going to be in the same equation. They'll balance each other. And then I'll make this in purple. That's my FTY. And I'll redraw this. That's my 400. Okay, so I put the Y components in purple so you realize that those Y components are all in the same equation. FV and FTY are pointed up, so they'll be positive. 400 is pointed down. That's going to subtract. So part B uses a different condition. It uses the condition for translational equilibrium. Not torque. Part B is the forces balance. So what have we got? We've got FH pointed to the right, so that's going to be positive. We have FTX pointed to the left, so that's going to subtract. What is FTX? It's just FT. Fine. You guys will get confused, so I'll put minus still. FT times the cosine of 40. I have FT. I just solved for it. That's the whole point of doing this part first. Find the FT, 310. Okay, so that works out to be 238. I think what they did is they carried an extra decimal. So this should be 311. Not going to make too much of a difference, but 238 newtons. I'll carry an extra digit. Do I need it anywhere else? I don't. I'll round off here. That's my FH. I'm not done. I have to find my FV as well. Okay, so that's, what did I do? I color coordinated the arrows in purple for my Y components. So I have my FV is up, plus my FTY, which is acting up, so they're both positive. And my 400 is acting down, so that's subtracted. That's balancing the other two. FV I don't have. FTY I can figure out. It's FT times the sine. I'll put the 400 on the right. AFT, again, I know what it is. I figured it out in part A. So 311 times sine of 40 is 200. FV is 400 minus 200. Or 200 newtons. Okay, but again, how did I solve FV and FH? I solved for FT first using torque. Okay, so we need to get a little extra practice, and I do need to explain the lab to you, but I can do that right after break. So let's do some more problems together. Let's take a look at 3. Same page. 3. Is that better at the back there, guys?
Yeah.
Better? Three. I'll set you up for 3 and 4, but I want to just read it first. Read over 3, and I'll supply you with the diagram. Okay, so where are you going to place the pivot? If in doubt, I'm going to leave the pillars out. They're there, but I'm simply focusing on the beam. If in doubt, place the, unless otherwise told, place the pivot on the very far left. It's attached to the wall. Usually it'll be on the left. Sometimes it's attached to the wall on the right. Place the pivot, in that case, on the right. Usually it's at one of the endpoints. Why do I do that? Why do I place it at the endpoint? I know that there's, let's draw it in. I know that there's an upwards force. Okay, that's the left, we'll call this F1. That's the force supported or created by the pillar or support on the left. That's the force due to support 1. Okay. If I place the pivot underneath there, you can, again, theoretically put it anywhere you want in your imagination. The torque is 0. There's no torque due to that force. Okay, there is another support on the right. I'm going to call that F2. Okay, F2 is 5 meters away. So there is a torque. F2 is a distance away from the pivot, so there is a torque. What are the other forces? You've got, obviously, in this case, the beam is not negligible weight. I'll put it in purple. So there is a weight due to the beam acting at the center. I'll call that, let's see, it's a 250 Newton beam. And that's acting at 2.5 meters. Okay, and then the person is standing somewhere here. Person is standing here. And he's 650 newtons. And the distance, I'm going to have to put it on the bottom here. I don't have a lot of room. His distance from the pivot is 1.5. Okay, so I'll start you off with that. The first question is, what's the force due to this? What's F2? That's the first question. Yeah.
What is F1?
F1 is, I didn't draw it in here, but there's a support here. There's a support here. The beam is on the supports, right? So the beam is putting forward or pressure on the supports, and the supports react with an upwards force each.
We don't know the value, right?
No, you don't know the values of either. But it's a trick. It's a trick. I told you, place the pivot here. That makes that torque here. That'll, in your equation, that will eliminate F1 in your first set of equations. But you'll have F2 in the equation so you can solve for it. Okay, so do that. Solve for F2 first using the condition for rotational equilibrium. Yeah.
In this case, there is no force in the external.
Yeah, good point. It's only wise. Yeah, Jake.
You're having 2.5s and 1.25 or 2.5?
You're having 1 point?
Oh, no.
Oh, you're sorry, right. I'll look for it now for you.
Thank you so much.
Yeah, yeah. I've got the main copy here if I have to make another copy. I do have a copy. I just- And you're.
Yes, that's right.
Done? Done, you guys are done? Need a little more
I have a
time?
question.
Okay,
I'm
so just as long as I get it in by the end so I can get the solutions. to it. Remember, all these angles are 90, right? It makes it easier on you. Yeah, this is clockwise. This is going to be negative. $325, 975. Okay, so I just calculated all the torques. I put my negatives in, right? So it's important that you get your negatives right. So how did I figure out the negatives? So anything that's clockwise is negative. I always imagine this pivot as being set in stone. It doesn't move, it sits there. The only thing that could, it's just the beam that could possibly rotate. In my mind's eye, it's not going to actually do that, but I'm imagining which direction it would be rotated by these forces. These would move it in a clockwise direction, so that's why I got my negatives there. These two torques are going to balance this torque here. This has to be in the opposite direction to balance it. So this force, if it was, again, this is fixed, if this was able to, it's not a pulling force, but if it pulled it, it would rotate it in the counterclockwise direction. Okay, so I have my condition for equilibrium. I have, and again, you could call these whatever you want. I call that T2, T3, T4, whatever you want. I just didn't want to use tau 1 because it's already used here. Whatever. So I have T or tau 2 plus tau 3 plus tau 4 is equal to 0. Remembering these are subtracted. I don't know what they did. So that should work out to be 320. Why is this equal to 0? It's kind of like, you know, when an object is, it's just sitting there and the force is balanced, you would say the net force is 0, right? So this beam, you can think of it, imagine it as having a pivot there, right? Imagine it being a freely moving beam with a pivot there. It could swing in either direction, right? So it's not obviously rotating. So it's similar to the net force being 0, because if the net force is 0, the object's not moving up and down. In this case, it's not rotating, so we can't speak of the forces being, we can't speak of the net force being 0, but that's not helpful. To solve for the force F2, we need to think of the torques being balanced because it's not rotating.
If it did move, then you'd have some.
If it rotated, then the net torque would not be 0. It's kind of like if an object accelerates, the net force is not 0. It would, a net torque would result in this accelerating in a circular path. Yeah. And the greater that net torque, the greater that acceleration is. Yeah.
There are two pivots Are they?
You can place the pivot wherever you want. That's one thing that's it's hard for people to grasp, but it's a theoretical concept, so you can place it wherever you want. It's most convenient to place the pivot underneath one of the forces. If you have two unknown forces, place the pivot underneath one of the unknown forces so that the torque is eliminated. Torque due to F1, torque due to F1 is 0. Okay? What does that do in the equation? Notice that in the equation here, there is no F1. It eliminates the F1 from the equation, which allows you to solve for the F2. Right? In math, you got one equation with one unknown you can solve for. If you have one equation and two unknowns, you can't solve for it. You need a second equation.
Just basically a graph.
Yeah, at this point, it's just algebra. Yeah. Okay. Am I done? You think I'm done? Is there a part B? We got 3 minutes left to solve for part B. Part B is what's the magnitude of the force on the left? Part B, there should be, did it copy? My. Really?
Oh, it's here.
Where? How the hell is, how the heck? Where is it? So it, what the frickin', okay, copied backwards, it is there, this page here. Okay, now, part B. Give it a try, we'll go over it in 1 minute, then you take your break. You take it at 10 too, it's not a big deal. You solve for F1. No, the torque is 0. The force is not 0. You said it earlier. There is no X component. There's only Y components. So what is that? 700, 900, 900, 600, 580?
Yeah.
580. Okay, different step for part B. Part B, you're using the condition for forces. You don't need the condition for torques in part B. I think we'll go right into the lab after break. So you're gonna have to be patient. I'm gonna give you a handout. You're gonna read it, and then I'm gonna set the lab equipment up. You're gonna have to work because we're kind of limited. You're gonna have to work in groups of 3, maybe 1, 2, 3, 4, 5, 6. So 3. Anyways, that's after break. Okay, so copy that down, and then we're taking a break. Oh, God. No?
No, but it almost.
Now, is that gonna work? I think it cancels it. Give me a second, I have to set it up again. There? I swear, some of you are super addicted to your phones. That's okay, I'm not gonna judge, because I'm kind of addicted to my computer. But what do you think of this? I've talked to my other students about it. I'm gonna set up a dongle you can attach your phone to with a suction cup to your forehead, so you don't even have to hold it. And the phone just kind of like right in front of you all the time. And if you're studying, you can there'll also be a swivel, so you just push it out of the way. And then when your teacher's not looking, you just push it back towards the center line. What do you think? Think I'm gonna make money?
Yes.
Yeah? No?
The dongle would be too long because like this is the standard position.
Yeah, whatever. I mean, it can be extended. You know, I'm gonna have version 1 is gonna be crap, and then I guess get everyone to pay for version 1. That'll help develop version 2, which will be your extension. What do you think? No? Not gonna make me my million? I need 2 million if I'm gonna buy another house in Vancouver. Oh well, I try. Okay, guys, take a break. Everyone got this down? Can I? Yeah.
Is it just like the reverse?
Okay, you guys.